Statistics Lesson 6.3, Sampling Distributions and Estimators. Two objectives. Develop the ability to describe a sampling distribution of a statistic. Determine whether a statistic serves as a good estimator of the corresponding population parameter. Definition. The sampling distribution of a statistic, sample proportion or sample mean, is the distribution of all values of the statistics when all possible samples of the same size n are taken from the same population. Sampling distribution of sample proportion. The sampling distribution of the sample proportion is the distribution of sample proportions p hat. That's what that symbol is the sample proportion, with all samples having the same sample size n taken from the same population. In other words, say you take a sample of 100, okay? And then you take another sample of size 100, and then another sample of size 100, until you've taken all possible samples of size 100 from the very same population. Okay, that's what they're talking about. Behavior or sample proportions. The distribution of sample proportions tends to approximate a normal distribution. The sample proportions target the value of the population proportion in the sense that the mean of all sample proportions p hat is equal to the population proportion p. The expected value of the sample proportion is equal to the population proportion. Let me show you what I'm talking about. Here is an example. What I've done here is, and I'll click on, I have used a random number generator to generate numbers between 1 and 6, what you would find on a die. Okay? Now, what I've done over here is this one counts the number of ones, that one counts the number of threes, and that one counts the number of fives. Okay. And this here is the proportions of 1, 3s, and 5s. So basically, I am getting the proportion of odd numbers on a die. Okay, odd numbers on a die. And in this particular one here, there were 2 5s, so that would be 1 or 2 out of 6 or 1 out of 3. Okay, now here is a chart of it, and you'll know I only did 10 samples. Well, it doesn't look anywhere near. It does not look anywhere near a normal population. But what if I do a bigger sample? What if I do, say, 20? Okay, well, that looks a little bit better than before. Let's see here. What if I do 50? That's a little bit more than 50. Yeah, that's about 50. What does it look like now? Well, that's looking better. Okay, notice as the sample size gets larger and larger. What if, say I did 100. Let's try 100. And let's go down here. And that's about 100, maybe 101. Okay, now it's looking even better. Okay, what if, say, we did? Let's go real big. We'll go to, say we go down to 500. Say we do 500 of these. And let's see. I have lost it. And let's see, we'll jump down here to 500. What happens when we have 500 of these? Maybe that's a couple more than 500. it back up here too. Okay, now it's approximating normal. Okay, now the number of samples is 500, and the distribution is approximating a normal distribution. So that's an example of the sampling distribution of sample proportions. Sampling distribution of the sample mean. The sampling distribution of the sample mean is the distribution of all possible sample means x bar, with all samples having the same sample size n taken from the same population. Behavior of sample means. The distribution of sample means tends to be a normal distribution. The sample means target the value of the population mean. That is, the mean of the sample means is the population mean. The expected value of the sample mean is equal to the population. And I did not, on the proportions. What should have been the proportion? It should have been targeting 0.5. And here it is. Here's 0.5 is right there. And so it was. Now, on the mean, what should the mean of these be? And I'm going to say it's probably about 3.5. And here on the proportion, it should have been 0.5. Okay, that, like I said, that's about right there. Here, the mean should be about 3.5. Okay, and here we got probably a sample of 10. I don't know why that's not showing. There we go, the sample. Here again, we got a sample of about 10. And you can see on a sample of 10 of those, it may not approximate normal. What if we jump it to, I didn't want, all right. And let's make it about 20. What happens to 20? Okay, it's a lot better. What if, say, we do 30? 30. Okay, again, now it's starting to approximate normal. And just for giggles, we'll go ahead and drop it down to 500 again. Just to show you what happens. When we get down here to 500, and take a look at it now. And now it is getting closer and closer, and 3.5 is right here, and that's the tallest bar. Okay. Sampling distribution of the sample variance. The sampling distribution of the sample variance is the distribution of sample variances S squared with all samples having the same sample size n taken from the same population. Behavior of the sample variance. The distribution of sample variances tends to be skewed to the right. Sample variances target the value of the population variance, that is, the mean of the sample variances is the population variance. The expected value of the sample variance is equal to the population variance. And I've got, I got one here for the variance too. Again, I just did 10 of them at first, and you can see it is definitely skewed to the right. And then if you add more to it, 20, okay, it's still kind of funny. What if you do about 30? It's still kind of funny. But you drop down here to 500. My Moby don't like to move it real quick. All right, let's go up here and let's go back up here. And you can see it's obviously skewed to the right. Okay, it's obviously skewed to the right. Now, why do we need to know that? Why do we need to know that? Estimators, unbiased and biased. An estimator is a statistic used to infer or estimate the value of a population. An unbiased estimator is a statistic that targets the value of the corresponding population parameter in the sense that the sampling distribution of the statistic has a mean that is equal to the corresponding population parameter. All right, now we need to know this because most times we don't really know what the true mean is, what the true proportion is, what the true variance is, or standard deviation. Okay, so we try to use unbiased estimators, such as p hat, the population proportion, x bar, the mean, and s squared, the sample variance. Biased estimators, the median is a biased estimator, the range is a biased estimator, and the standard deviation is a biased estimator. Now, the standard deviation does not target the population variation sigma, but the bias is relatively small in large samples. So the sample standard deviation S is often used to estimate the population standard deviation sigma, even though the sample standard deviation is a biased estimator of sigma. Make sure you put this stuff in your notes. Why sample with replacement? One, when selecting a relatively small sample from a large population, it makes no significant difference whether we sample with replacement or without replacement. Two, sampling with replacement results in independent events that are unaffected by previous outcomes, and independents are easier to analyze and result in simpler calculations and formula. So that's why we sample with replacement. Again, this first one here, number one, is really big, okay? If you have, and we'll just try. All right, say you have a population of 10,000. And we talked about earlier the 5% rule. If you're less than 5%, so 5% of 10,000, we'll just go to calculator. And 10, 1, 2, 3, times 0.05, that's 500. That's a lot of samples. If you're only pulling 400 samples from that, it's not going to make a whole lot of difference. Think about it. One, control, divide 10,000. And then how about one, control, divide 9,999. There's not a whole, let's go up here and we'll go up here and grab that and make a decimal. And then we'll go up there and grab this one. you have to go there's 4 places. You have to go 5 places. Or, and we'll just, let's see, settings, document settings, float 6. We'll just change it to float. Okay. Now let's go up there and grab this. And one control divide 10,000. I hate when it does me that way. Well, let's see here. Doc. I hate when it does me that way. Float, we'll say float 10. Now, control. All right, 4 places. 1 control divide 9,999. And there you go. Okay, that's not a whole lot of difference. Okay, so why go through all the extra stuff? Great job, folks. See you tomorrow in class, and have a wonderful evening.